Okay, so good evening, everyone, and I welcome you all to today's live session of Nonlinear Vibration NOC25 me57. This course is being taught by Professor S.K. Dwivedi, IIT Guwahati, and I'm Rasha Aditi Ranjan, NPTEL PMRF TA in the Department of Mechanical Engineering, IIT Patna. And we have already completed 7 live sessions corresponding to the lectures that has been taught in the previous 7 weeks. And today we will discuss about the questions related to all the 3 lectures that has been taught in this week, and so that it will be helpful for you to solve the assignment problems. So we'll begin with the overview of what has been taught this week. So again, we discussed about limit cycles this week using the van der Pol equation, and we got to know that the van der Pol equation, if we change the parameter which is multiplied with the damping term, a limit cycle can get converted into relaxation cycle. And then there was discussion about what is the difference between limit cycle and relaxation cycle, and what are the characteristics of relaxation cycle. About limit cycle, if you remember, limit cycle is nothing but isolated periodic orbit. If you remember, like for a spring mass system, if I give a small perturbation, the system is going to show periodic oscillation. If I change the value of perturbation, the amplitude of periodic oscillation changes, right? But for the case of limit cycle, it is the only periodic orbit in the state space. So even if I start my system from inside of the limit cycle or from the outside of the limit cycle, it is always going to converge or diverge to reach to the limit cycle. Okay. So limit cycle essentially exists in real world, and it is very important to study. And for the van der Pol equation, limit cycle, if we changed the parameter, it got converted into relaxation cycle, which had like, two kind of, we say, time scale, because when we saw the velocity plot, we got to know that for a certain period of time, the velocity profile was vertical, and for the other period, it was horizontal. Okay, which means that the position was changing very rapidly when the velocity profile was vertical, and it was changing very slowly. The velocity profile was horizontal. By vertical and horizontal, I don't mean exactly 0 degree or 90 degree, but we can say almost. Okay, like 1 degree, 2 degree, or 88 degrees, 89 degrees, like that kind. Okay, so essentially one period uh, was essentially divided into 2 parts, where once there was a very rapid change of the position, and for the other time the change was very slow. Okay, so that was what we call relaxation cycle, and it's just depend on the value of the parameter, which we will see further in the question. Then discussion was done about existence of closed orbit, where 3 types of criteria was introduced. One was the gradient system, Dulac criteria, and the Lyapunov function, which there were certain equations or there were certain laws. Like for example, for the gradient system, it was said that you know like for example, if I write x dot is equals to f of x comma y, and y dot was equal to g of x comma y. So if my system satisfies partial differential of x with respect to y and partial differential of g with respect to x, if this is satisfied, then we say that the closed orbit are impossible. Okay, so this was my gradient system. Then we had the Dulac criteria, which said that if my system was able Okay. Likewise, was the Dulac criteria, where we could tell about whether my system is going to have a closed orbit or not. Likewise, there was Lyapunov function, which said that for a system, if I'm able to define a Lyapunov function, then the closed orbit will not exist, right? So these were the criteria which you can use if you're solving a practical problem where you have the equation of motion. Then you can apply these criteria of function, and then you can predict whether my system is going to have a closed orbit or not. Third one was the stability and bifurcation of periodic responses. So, you remember till now we were discussing about the fixed point response and the bifurcation of the fixed point response and the stability of the fixed point response. If you remember, like for a fixed point response, we used to say whether my system is stable, unstable, or the fixed point is a center, or it's a spiral in, spiral out. It would all depend upon the value, like the eigenvalues. So like for the nonlinear system, we computed the Jacobian, and then we find out the eigenvalues. On the basis of the eigenvalues, we were able to tell whether my fixed point was stable or unstable, right? And then again, using the equation and the eigenvalue, we again started to talk about the bifurcation that is happening in the system. Okay, so like for example, during the bifurcation, if I change the parameter, and I see that okay, with the changing of parameter, the number of equilibrium points that exist changes, or its stability changes, then in that case we used to compute the eigenvalue and then tell that okay, which kind of a bifurcation occurs in the system. But till now we were just talking about fixed points, right? But what about the periodic responses? Like for example, a periodic response can be stable or unstable, right? It could be neutral also, right? And apart from that, like for example, if I talk about a spring mass system, so if I give a certain perturbation, the periodic orbit it is going to trace, is it stable or is it unstable? None, it is neutral, right? Because from that perturbation, if even if I change a very small amount, it is not going to diverge, neither it is going to converge. It is going to have the amplitude related to the change in initial condition. Okay, the amplitude is going to change, right? But if I talk about a limit cycle, it is stable, because even if I change the initial condition, it is always going to converge to that limit cycle, right? So likewise, it is important that we study about the stability of the periodic response. And as I introduced also in the last question that I discussed previous week, that how using the Floquet theory we can actually predict about the stability of the periodic orbit, right? And then we studied about the bifurcation of periodic response, like similar to that of the fixed point response. The periodic response can also show different kind of bifurcations, which we will discuss further. And in the end, chaos was introduced. However, we have studied briefly about chaos when we did the initial week's live session. But here, more elaborately, chaos was discussed. What are the characteristics of chaos? And should we avoid chaos? How chaos is achieved? How does chaos look like? How to say whether my response is chaotic or not? All those things were discussed. Okay, so this is what we did get to know by seeing the lecture, and now we will start the questions. So coming on to question number 1. It is given that for this system given as we have a 2 degree of freedom system, with the first order differential equations, which type of bifurcation occur at the origin? Okay, I think now we are good to go with the kind of bifurcation that occurs, right? So first we will try to analyze in the way we did earlier also, like finding the Jacobian, putting the value, and then see how the system is behaving. Okay, so we'll assume this is F2, we'll assume this is F1. So we can write Jacobian as partial differential of F1 with respect to Fx, partial differentiation of F1 with respect to y, partial differentiation of F2 with respect to x, and partial differentiation of F2 with respect to y. Okay. Now if I compute the Jacobian, what is it going to be? So first I will differentiate x dot with respect to x. I'm going to get mu plus y square. Then if I differentiate x dot with respect to y, minus 1 plus 2xy. Differentiating y dot with respect to x, 1, and y dot with respect to y, mu plus 3y square. Now it is already given which type of bifurcation occur at the origin. So definitely we have to put x is equals to 0, y is equals to 0. Is equal to mu minus 1, 1 mu. Okay. Now we'll compute the eigenvalues. So for computing the eigenvalues, we'll have to find out j minus lambda I determinant is equal to 0, which implies mu minus lambda minus 1, 1, mu minus lambda is equal to 0, which implies mu minus lambda square plus 1 is equals to 0. So we have mu minus lambda square is equals to minus 1, mu minus lambda is equals to plus minus iota, where iota is nothing but under root minus 1, imaginary value. So my lambda is going to be mu plus minus I, which is a pair of imaginary root. Pair of imaginary root. Okay. So from this I get to know that my 0 comma 0 is going to be what? It is going to be a stable spiral if my mu is less than 0, and it will be unstable spiral if my mu is greater than 0. Correct? Because the presence of imaginary root means that I'm going to have a oscillating behavior, right? If my mu is 0, I will see that my system is going to have a oscillation, right? Because it has a pair of imaginary root with a real value is equal to 0, right? If my mu is less than 0, right, then I'm going to have my real value negative. And we have discussed it earlier also that if my real part is negative, if the real part of my eigenvalue is negative, it means that my system is going to converge. It is going to have a spiral in kind of behavior. Okay. Now, if my mu is greater than 1, sorry, greater than 0, what is going to happen? In that case, my system is going to have a divergence from the fixed point. Correct? It is going to show a divergence. Okay. And spiraling out behavior. Okay. But what is important to note is that at mu 0, I have a periodic orbit. Correct? Because at that time, we are going to have plus minus I as the eigenvalues. So I'll just write it. If mu is less than 0, if mu is greater than 0, the behavior is spiral out. Okay, like this. And if mu is equal to 0, periodic response. Okay, I hope this is clear. Now, if you remember in the previous week's lectures or uh, before that, we discussed, and it was taught in the lecture also, that there were various, criterias to determine that whether my bifurcation is static or dynamic, and if it is dynamic, whether it is hop or bifurcation or not. Okay, so if you remember the criteria, was that the first okay, we'll just write it. The first thing was that the function f at x naught and mu c should be equal to 0. Okay, so we have two functions. One is my f1, which is equal to mu x minus y plus xy square. Mu x minus y plus xy square. And f2, which is equal to x plus mu y plus y cube. Okay, so we have to find f1 and f2 at mu c and x naught. Now I know that my critical value of parameter is 0. Why? Because the change of the uh, stability actually happens at 0 value, right? Before 0, my 0 comma 0 is stable. After it, it becomes unstable. So mu c is equal to 0 and x naught 0 comma 0. So if you put it in these two equations, what will you see? Your f1 is equal to 0 and f2 is equal to 0. So my first condition is satisfied. Okay. Now second condition. So wait, first let me write one thing here. A bifurcation was static and a dynamic. Dynamic bifurcation was hop bifurcation and static had saddle node, transcritical, and pitchfork. These were the type of bifurcations. Now the second, if you remember, the second condition was talking about the eigenvalues. Okay, so what did we do? We had to compute dx into f, and then we have to find the eigenvalues. And once we get the eigenvalues, then on the basis of that, we will get to know whether we have to proceed with the static bifurcation or we have to proceed with the dynamic bifurcation. So we'll find out the okay, we already have the Jacobian. Sorry, and we already know the lambda. What is it? It is mu plus minus I. So what do we have? We have a pair of imaginary eigenvalue. Pair of imaginary. Reminded, these are the eigenvalues. These are computed for the Jacobian matrix. Okay. So pair of imaginary eigenvalues. So if you remember, a pair of imaginary eigenvalue was there in the case of hop bifurcation, right? Not for the static bifurcation. So if this is the case, then it means either it is going to be a hop bifurcation or not. Okay. So there was a third condition. If you remember, there was a third condition which was transversality condition, which said that if my at mu is equals to mu c, if my lambda is of the form a plus minus ib, okay, a plus minus ib, then the transversality condition says that the differentiation, partial differentiation of a with respect to what? With respect to the parameter mu. If it is not equal to 0, if it is not equal to 0, then this means that the eigenvalues cross the imaginary axis with non-zero velocity, crosses the imaginary axis with non-zero velocity or speed. So if that is the case, it means that while at mu c there is going to be a periodic orbit. And if these all the three conditions are satisfied, it means that the bifurcation is Hopf bifurcation. Okay, so this is the transversality condition, which means that the eigenvalues cross the imaginary axis with non-zero speed. So now we will see whether my system is satisfying this or not. So if I look at my eigenvalues, it is nothing but mu plus minus I. So if I compute differentiation of mu with respect to mu, this is going to be nothing but 1, which is not equal to 0. So my transversality condition is also satisfied for the given equation. So since my second condition is also satisfied and the third condition is also satisfied, which means that Hopf bifurcations occur in the system when my parameter changes from negative value to positive value. Okay, so for question number 1, okay, now I have among the Hopf I have to select whether this is supercritical, subcritical or degenerate Hopf bifurcation. Okay, so it is going to be any one among the three. So firstly, what is a supercritical Hopf bifurcation? So if you remember our supercritical bifurcation, which we used to study for the fixed point response. So there was a fixed point. Initially, there was only one fixed point, and then after the change of parameter, there were three fixed points, among which the fixed point which was there before the critical parameter used to get what? It used to get unstable, and the two new solutions used to get stable. Okay, so that was my supercritical supercritical pitchfork bifurcation. But if we talk about this Hopf bifurcation, so if you remember that there was change and one stable fixed point changed to two stable fixed point and one unstable fixed point. Correct. In this case, what am I seeing? I'm seeing that initially I had 0, 0 as stable. Now it becomes unstable. Okay. But is there a, a new orbit that occurs? Two new orbits that occur? Well, that is not the case over here. And it is very evident because my system gets unstable. Right. So this is not a case of supercritical Hopf bifurcation. Okay. So then there are other two responses, which is a degenerate and the other one is the subcritical. If we talk about the degenerate Hopf bifurcation. So degenerate Hopf bifurcation is something where there is a disappearance. Okay, there is a kind of disappearance which is not true over here. Okay, so this is actually a critical Hopf bifurcation because the first two cases are not possible. So it is definitely a subcritical Hopf bifurcation. Apart from that, since you see this is in the Cartesian coordinate, if you change it in the polar coordinate, that you will then you will get to know that okay, how my radius is changing. See, because 0, comma 0 is a trivial state where my radius is going to be 0, but I'm going to have other radius values as well, but I will get to know that I get a orbit, but it is essentially not stable. Okay, so if I start inside that orbit, I'll diverge. If I start outside that orbit, I'll diverge. Okay, because that is a unstable cycle. Okay, and if there is an unstable cycle that occurs, then it is a what? It is a subcritical Hopf bifurcation. Okay. Coming on to question number 2, where we will be talking about Poincare section. Okay, so till now when we were talking about how to show the response of a system, see, in case of supercritical Hopf bifurcation, what is going to happen is like in case of fixed point response, when we had a supercritical bifurcation, what was happening? There was one fixed point, right? Then we had a change of the fixed points, right? And the change of fixed points was such that there were now three fixed points, in which two were new and the one was same as the previous one. Okay. And what happened? That the initial fixed point, which was stable earlier, got unstable, and the two new points got stable, and the first one got unstable. Right. Similarly, if we talk about dynamic case, it should be such that there should be two or at least one orbit, okay, that would occur, at least one orbit that would occur and make my system stable. But as you can see over here, that is not going to happen. Okay, that is not going to happen over here. So that is what a supercritical Hopf bifurcation. Basically, if I try to plot, it is something like if I change the parameter, this is the case of my supercritical Hopf bifurcation, and this is going to be my subcritical Hopf bifurcation. I hope this is clear. Next, we will come to question number 2, where we talk about the Poincare section. Okay, so what is Poincare section? How it is important? So, as I said, that my if I talk about that, I want to plot my response, and I want to know what are the characteristics of my response. So, what I used to do, I used to plot the time response. I used to plot the phase plot, right? These were the thing that I was doing. But then, if my system is linear, I'm going to have periodic response, right? Now my system has become nonlinear. It could have possess a property like periodic solution, quasi-periodic solution, periodic solution with a different kind of a time period, right? I could also have a chaotic solution, right? If that is the case, then how am I going to differentiate? Okay, how am I going to differentiate? So the concept of Poincare section was introduced to reduce one dimension from the system. Okay, to reduce one dimension from the system. Like for example, if I have a 3D plot, okay, and I want to reduce one dimension, what will I take? I will cut the 3D plot in a plane, and the points that I'm going to get in the plane, I'm going to just plot it. Right. For example, if I have a solid sphere, I have a solid sphere, and I don't know how the internal what is the internal structure of the sphere. Like for example, if I have a solid sphere and I have a hollow sphere. Okay, I have a solid sphere and then I have a hollow sphere. From outside, if I cannot like pull it up. It is just kept. I have to just see and tell. Let us say that I have to just see its drawing images and I have to tell that whether it is a solid sphere or is it a hollow sphere. You see from the outside, the surface is the same, the radius is the same, the both the spheres look like same. So how am I going to differentiate whether it is a solid sphere or a hollow sphere? So what will I do? When I have a 3D plot, I'm going to what? Section it. I'm going to section it. And if I create a 2D section, I will cut from the center. Okay, I'll get that for the solid sphere, I'm going to get the surface like this. And for the hollow sphere, I'm going to get the surface like this. And through this, I can differentiate whether my sphere is solid or hollow. Correct? So what have I done? I have converted my 3D figure into 2 dimension, right? So it was able to tell me about the property of the system, which I could not tell about just by merely looking at the sphere, right? Similar to this, when we talk about the response of the system, if we reduce one dimension of the system, then I could know that what is the two-dimensional behavior of the system, right? And with that, it would be easy for me to know about my system. Okay. Like for example, just a second. Like for example, okay. Like for example, I have two periodic response. For a system, I have equation of motion, something of x double dot plus f x comma x dot, where f is a nonlinear equation, and then I have f sine omega t. Okay. Now it is given that for f1, the plot is something like the phase plot is something like this. Okay, and it is periodic. I can see that. Now for f2, the plot is something like this, or we can make it like something like this. This is for f2. What I can see is that both are periodic, but there is some change in structure in the phase plot, right? There is some change in structure. Let us say I also draw for some f3. Okay, and it is something like this. This is also periodic. Okay, it is repeating itself after a period. But now the question is that all the three responses are periodic, but then what is the difference between these? Visually, I can see that there is some difference. Okay, the number of loops that are present and it is different. So now, if I get the opportunity to cut this, okay, I want to reduce one dimension from the system, okay, then I can know that, okay, what is happening internally in the system. So what will I do? I will plot the Poincare section. Now, what is a Poincare section? Poincare section is actually obtained from the phase plot or the response of the system, and we actually reduce one dimension. How do we reduce one dimension? See, for a 3D figure, we used to take a plane, correct? And using that plane, we used to know what are the internal characteristics. So with this kind of system, what we can do is we can either find the all values of x where the velocity is 0. We can find all values of x dot where my position is equal to 0. Or what I can do, 0 is just an example. I can take any constant value. And third one is that I try to take the points after a certain interval of time. Basically, what we do in the stroboscopic effect, we use a stroboscope to send the light to a system. I hope you people have seen that experiment, that we take a scale and we try to oscillate it, and then we send, and we want to know that what is the frequency at which the scale is vibrating. So we use a stroboscope and we start changing the frequency at which the light is being given to the scale, and the moment I see that for the frequency my vibrating scale appears as in a static state, okay, then I say that okay, my scale is having this frequency, because the frequency at which the scale is oscillating and the frequency at which the stroboscope is sending the light, it actually matches. Okay, similar to that concept, what do we do after a certain interval of time? What do? We try to find out that what is the response of the system. So what do we do? Like for example, I have the data x dot and x for okay, and then I have the time. Okay, and I know the time period, which is nothing but 2 pi by omega. Why am I taking 2 pi by omega? Because my system is a damped system. I have the damping present, and we know that if the damping is present in the system, my system is going to possess two kind of vibrations. One is that because of the natural frequency of the system, which is going to be introduced because of the change of the initial condition, and the second one is going to be because of the forcing function, right? Now, since my system is damped, the component of the natural frequency, it is going to die out with time, and in the steady state, I'm going to take the t as 2 pi by omega. Okay, and then what will I do? I will now, since I have this data, let us say this data 0, t, 2t, 3t. What will I do? I will take the data after every t, capital T, after every time period, I'm going to take the data. Like I take at 0 value, I take at t value, I take at 2t value, I take at 3t value. And I'm going to plot it in the phase plane. Okay. So I'll see that when I do it, for this figure, I'm going to get 1 point. For this figure, I'm going to get 2 points. And for this figure, I'm going to get 4 points. Okay. So my time period for F1 was T. My time period for F2 was what? 2T. And my time period for Ft was what? 4T. Right? So what happened? It changed from T to 2T and from 2T to 4T. Okay. So in that case, what did I get to know? I got to know about the time period of my oscillation and the relation between the time period with respect to the period of forcing. Right? By merely looking at the phase plot, I cannot talk about the time period. But now since I've obtained the Poincare section, now I know that my response is periodic or not. Okay. So the question says that the Poincare section of a periodic response can be, it could be 1 point, it could be 2 point, it could be 4 points. All the first three options are correct. All the three options are absolutely correct. Okay. Now, here I got to know very little about something. Okay. Now let us go to this third question, which will introduce the main use of Poincare section. So it says that the Poincare section of a chaotic response can be, for a periodic response, I know it could be finite number of points. Okay. Now if I talk about a quasi-periodic response, quasi-periodic response. So for a quasi-periodic response, you'll see that my Poincare section. Okay, wait. There is one more thing that I want to tell over here. For example, if my solution is going to have multiple frequencies, for example, my solution is something like 4 sine of 5t, 6 sine of 7t, 10 sine of 9t. So for this system, what would be the time period? So for this kind of case, we take the minimum possible time period, which means my time period is going to be 2 pi by 9, corresponding to the highest frequency. Okay. Likewise, for quasi-periodic response, the Poincare section is going to be nothing but a closed loop, something of this sort, or maybe something of this type, two loops is also possible. Okay. So for the quasi-periodic response, the Poincare section is going to be a closed loop. Fine. How about chaotic response? See, for the chaotic response, if we talk about the response with respect to time, what is it? It is just random. Okay. Now, if I start cutting my system at t, after every t value, t, 2t, 3t, and if I check the points, and this, you see all these 4 points, they are not related to each other. They are in no way coinciding with each other. So when I plot the Poincare section, I'm going to get a random distribution of points. I'm going to get random distribution of points. And these random distribution of points in the phase plot shows that my response is chaotic. That my response is chaotic. So one of the major usage of my Poincare section is to see whether my response is actually chaotic or not. Okay. So if I have a random response, okay, and I'm not able to predict whether it is periodic or it is chaotic. So what will I do? I will plot the Poincare section. If my Poincare section is showing a closed loop or just finite number of points, uh, then we can say that okay, it is either quasi-periodic or periodic. But if it's something like this, there are multiple points that are distributed randomly in phase plane, then we say that my response is chaotic. There is also one interesting thing that there is always a periodicity in chaotic motion. When I say that, what I mean is that if my system is having some kind of damping present in it, okay, and then when I try to find out the Poincare section, it is going to show me the presence of a strange attractor. Okay, so like for example, in case of fixed point response, I say that my fixed points act as a act as an attractor or a repeller. If it is stable, it's an attractor. If it is unstable, it will act as a repeller. It is going to repel the response from itself. If it's an attractor, it is going to like the system is going to try to reach that fixed point, right? For the periodic response also, we can say that my periodic response could be stable or unstable. If it is stable, it is a attractor. If it is unstable, it is a repeller. But we already know about fixed point and periodic response. But in case of chaotic motion, I get to see that okay, there is some kind of a pattern, something is there. Like this is the random distribution. What if the distribution is something like this? Something like a fractal we'll have. Okay, fractal means snow. If you take a snow particle and if you start like focusing on the snow, as you will go towards the intricate structure of the snow, you will see that there is a self-repeating structure. Like we have in cauliflower, if you take a whole cauliflower and you break one side, then also you are going to have same kind of structure. Again break it, then same structure. Something like fractals. So you'll see that a fractal kind of a behavior you can see that we call as a strange attractor. We call it strange. Why? Because we don't know about it till now. This is something new that acts as an attractor, and we call it a strange attractor. So for chaotic motion, with for a damped system, we can often see the existence of a strange attractor, and that is why, because of the presence of this strange attractor, my chaos has a very nice property of boundedness. You see, chaotic response could be random. It could go anywhere with respect to time. It has very high sensitivity towards initial condition, but it is always bounded. It never lets my system go to infinity, right? And that boundedness is because of the presence of a strange attractor, because there is an attractor, and my system is always attracted towards the attractor. It is always there with the attractor, and that is why it is never going to go to infinity. Okay, so the question says that the Poincare section of a chaotic response can be random points. If there would have been an option of strange attractor, that would also be correct. Okay, now we'll come to question number 4. Okay, so for a system, if the flow K multiply leaves through -1, then which type of bifurcation occur? Okay, so in the previous class, as I discussed, that if I have a system with equation of motion something like x1 naught is equals to f of x comma x1 comma x2, and x2 dot I have f of x1 comma x2. Okay, so from this what I can uh, understand, from this I can understand that my system is going to have free oscillation, right? Because there is no forcing present and there is no damping as well. So however, it is applied for the damping case also. I'm just taking an example. So if my system is of this form, okay, and then if I give it some initial perturbation, okay, then what is going to happen to my system? My system is going to show, let us say, some periodic response. If it is nonlinear, I will give the perturbation value very small. Since for very small perturbation value, my system is going to show the periodic response. Okay, so let us assume the solution for initial condition x1 at 0 and x2 at 0 is periodic. The solution we are assuming as x1 0 and x2 0. Okay, we are assuming as x1 0 and x2 0. This is periodic. Okay, fine. We are very good in computing the Jacobian, correct? Earlier, we used to compute the Jacobian about a fixed point. This time, we are going to compute the Jacobian around a fixed orbit because we have x10 and x20 as periodic. Okay, so we'll assume small perturbation y1 and y2 from the periodic response x10 and x20 respectively. Okay, done. Now what? We'll apply the expansion method and everything. So we can then convert a system as y1 not p1 y1, p2 y2, y2 dot as p3 y1, p4 y2. Okay. Now it can happen, definitely it is going to happen that my p1, p2, p3, p4, anyone could be a term which is dependent upon x10 or x20. If my x10 and x20 is periodic and my any of this is a function of that, then definitely any of p1, p2, p3, p4 could be periodic with time. So now what? Now this becomes a parametrically excited system because the parameter is actually periodic with some time period, right? So I can write y10 is equal to a into y. Now with the parametrically excited system, I know the Floquet theory, right? Because the Floquet theory is applied for a parametrically excited system and it tells about how my response of the system is going to be, whether my system is going to have a stable response, whether it is going to have unstable response, it is going to have a periodic solution. The periodic solution is going to have time period same as that of the uh, time period of the parametric excitation or twice of that. We could tell about it, right? But now this y is essentially the perturbation from the periodic solution. So if my system, this y is stable, it means that my system is going to again converge to the periodic response. If it's going to converge to the periodic response, I can say that my system is stable or not, correct? So on the basis of that, we can also talk about the bifurcation. If you remember earlier also, we were using Jacobian to tell about the stability of my fixed point, and then we again used the concept of Jacobian to find out about the uh, stability. Okay, and the bifurcation as well. For the bifurcation, kind of bifurcation, we were using the Jacobian and the eigenvalues that is obtained from the Jacobian. Similarly over here, now we'll be using the Floquet multiplier to predict about the stability, and then we are again going to use the Floquet multiplier to predict about the bifurcation of the system. What kind of a bifurcation is going to occur if my parameter is varied? Okay, I hope that is clear. Now I have my equation. I know how to compute the Floquet multiplier that we have already discussed. Okay. Now we'll talk about that how and what kind of a bifurcation is possible and how we are going to know that. Okay. Now, if you remember, my Floquet multiplier used to be inside the real axis, imaginary axis. This was 1, this was minus 1, this was I, this was minus I. If my Floquet multiplier was inside, my system was stable. If it was outside this circle, it was unstable. Alright. So now, when I vary the parameter, my Floquet multiplier is going to change. Correct. So depending upon how my Floquet multiplier is leaving this circle of radius 1, I can talk about the bifurcation. Like for example, my system was initially stable, which means that my Floquet multiplier was inside the circle, right? Then my system was what? Stable. Now when it comes out of the circle, it will get what? It will get unstable. Or there could be occurrence of, see, when I say unstable, the current cycle is getting unstable, but another cycle can be created, right? Because I'm talking about a periodic orbit. If that periodic orbit is unstable, that doesn't mean that my system is going to diverge to infinity, right? I'm talking about in a close vicinity of a periodic solution. If I'm saying that the periodic solution is stable, it means that my system is going to be there for the small perturbation. If I'm saying that my periodic solution is not stable, it means that my system can go to infinity, but there is a possibility that there could be another response, another periodic orbit, quasi-periodic orbit, anything could be possible. Chaos, that is also possible. So firstly, if my flow K multiplier is equal to 1, okay, not 1 actually, if one flow K multiplier is equal to 1, okay, in that case, I'm going to say that my periodic orbit is hyperbolic periodic solution. If more than one flow K multiplier is equal to 1, then this implies that my periodic solution is non-hyperbolic periodic solution. I can have, multiple degrees of freedom. Now, if I have 3, 4 degrees of freedom, then I'm going to have 3 or 4 eigenvalues. In that case, if 1 is equal to 1 of the flow K multiplier, we are going to say hyperbolic periodic solution. If more than one flow K multiplier is equal to 1, then it is going to be non-hyperbolic periodic solution. Okay. Now, if I talk about with change of critical parameter mu, comma, first case, Fm leaves through 1, which means if this is the real axis, imaginary axis, if my flow K multiplier is leaving from here, then what are the possibilities that can happen? So there are 3 possibilities of the bifurcation that can occur. Okay. First one is the cyclic fold bifurcation. Okay. Uh, okay, wait. If I plot the radius with mu, it is something of this type. A. No, let us call this as A. Okay. Uh, do you remember saddle node bifurcation? This is not saddle node actually, but you can use the analogy to remember. So in the saddle node bifurcation, there was no equilibrium points or fixed points. And with the change of parameter, there was sudden occurrence of, a pair of fixed points in which one was stable and the other was unstable. Also, there were two fixed points, one stable and one unstable. And when I changed the parameter value, they both came together, made a half stable fixed point, and after that disappeared. Both were considered as a saddle node bifurcation. Remembering that analogy, remember this cyclic fold bifurcation. Here, R is the radius. There could be two possibilities, one stable or radius and the other unstable radius. With a change of parameter, it may happen that both come together, collide and disappear. This is my cyclic fold bifurcation. Okay. So we can say that stable, one stable and other unstable orbit come together and leads to disappearance with change of mu. This is your cyclic fold bifurcation, and this is a very catastrophic kind of bifurcation, because you see initially there was if we call it mu c, before mu c there was one periodic orbit, but as soon as I cross mu c there is no periodic orbit, and hence my system is going to be failed. Okay. There could be a possible case of cyclic fold bifurcation, that instead of going to a catastrophic failure, the system can also go to chaos or to disappearance with change of mu, or can lead to chaos after mu c. Mu c. Okay, and this we call as intermittent transition of type 1 chaos. Clear? Okay. Second, we'll come to the second one, which is symmetry breaking. You remember the pitchfork bifurcation? Follow the same analogy. There was once a periodic orbit, stable periodic orbit for mu less than mu c, and as soon as I cross mu c, the stable periodic orbit becomes unstable, and there is occurrence of two new periodic orbits. This is for mu greater than mu c. Unstable, stable, new, stable, new, and this was unstable, old. Symmetry breaking bifurcation, similar to the pitchfork bifurcation. And again, similar to the pitchfork bifurcation, there could be supercritical or subcritical. This is definitely supercritical, subcritical. Remember earlier we on the y-axis we used to have fixed points. Now on the y-axis we are having the radius, and on the x-axis it is the same, the bifurcation parameter. Sorry, it should not be mu c, it is just mu. I hope this is clear. Very easy. Then we have a third kind. We remember the transcritical bifurcation. Similar transcritical bifurcation. What do we do? What do we had in case of fixed points? The number of fixed points were not changing. Unlike saddle node and pitchfork, where there was a change in the number of fixed points, in transcritical bifurcation, the number of fixed points used to be the same, which was equal to 2. The only difference was that as soon as we cross the critical parameter, my stability characteristic of the fixed points used to get exchanged. If one was stable earlier and the second was unstable, there will be a change of the behavior. The first one will become unstable and the second one will become stable. That was the transcritical bifurcation. Similar to that is this case also. We are going to have two radius and two corresponding to the parameter mu. So like this and this. Okay. So this was line 1, this is line 2. So you see that this was earlier before mu c. This line was stable, and after mu c it becomes unstable. And if I look at the second line, earlier it was unstable and now it becomes stable. So what has happened? There is a change of the stability of the periodic orbit. Okay, there is no change in the number of periodic orbit, but just the change of the stability of the periodic orbit. So this is going to be the transcritical bifurcation. So when my flow K multiplier leaves the unit circle through the real axis, then there are three cases of bifurcation that could occur, which you can test by using MATLAB also. That you can, what you can do is analyze the system before mu c, analyze the system after mu c, and then you are going to get to know that which kind of a bifurcation is occurring. Okay, there could be three possible cases where we had cyclic fold bifurcation, which we will remember by remembering the saddle node bifurcation. Second one was symmetry breaking, which we will remember by remembering the pitchfork bifurcation. And third one was the transcritical, which definitely we'll remember by the transcritical bifurcation, which we studied for the fixed points. Now coming on to if Fm leaves through -1. So if my flow K multiplier leaves my unit circle through -1, which means that real and my flow K multiplier is leaving from here, then there was only one case, which was the period doubling. Period doubling bifurcation. Okay, so what is going to happen over here? Earlier there was a periodic response which becomes unstable and it disappears, and there is occurrence of a new periodic response which has a time period which is equal to twice of the time period of the earlier periodic cycle. So the periodic response disappears with change of mu, and a new periodic orbit generates with time period twice the time period of the earlier periodic cycle. Clear? Very easy. We already discussed how we can know whether the time period is T or 2T by looking at the Poincare section. Okay. Third, if Fm leaves the circle going away from real axis, which means something like this. Definitely there's going to be two arrows because my flow K multiplier, if it is imaginary, it is always going to exist in pair. Okay, then it is going to be a secondary hop bifurcation. Okay, anyways, for the period doubling, there are two options. One is the supercritical case. There is a stable branch occur with 2T, sorry, 2T, and another is the subcritical where unstable 2T branch disappear. Okay, now coming on to this, we have secondary hop bifurcation. So secondary hop bifurcation, what is going to happen? A hop bifurcation is going to occur, okay, and the change, like the initial orbit is going to get what? It is going to get unstable, and the new orbit is going to come, which may be periodic or it could be two period quasi-periodic. Okay, new periodic orbit or two period quasi-periodic can occur. Now these are the possibilities that are possible. Okay, so if I look into the question again, for a system with the flow gain multiplier leads to -1, then whichever type of bifurcation occur. Now I know the solution is going to be period doubling. Coming on to question number 5. Secondary hop bifurcation may be observed if the flow gain multiplier leaves the unit circle through complex conjugate away from the axis. Okay. Question number 6. The intermittency of chaos in the system response may lead to chaos. Okay. What the question is trying to say that I have a periodic response, but in the periodic response, for some time, some chaotic response is there. Okay, for a particular parameter. So can it lead to chaotic, wholly chaotic response? So what happens is that okay, I have a periodic response. Okay. Now in this, if for a certain time, let us say over here, what happens? Chaos is there. This time there is chaos. Okay. Now is this going to lead to chaos? See, for chaos to happen, chaos doesn't happen suddenly, firstly. There's always a parameter value for which chaos is going to exist. And there could be a, for that parameter value only, there could be a set of value for which chaos is going to exist. And for some set, the chaos is not going to exist. Okay. So it is important that we first talk about the route to chaos. Okay. There could be many routes that could lead to chaos, to be honest. There are many that has been discussed through papers, books, and there are many that are still yet to be discovered. Okay, but we'll talk about only three most uh, popular one. Okay, we'll go to the new slide only. Now we will be talking about route to chaos. Okay, the first could be Period doubling. Period doubling, what is period doubling? As per the name suggests, that there is doubling of the time period. Okay. So if I try to write it mathematically for the critical parameters mu k, for the critical parameters mu k, where k is equal to 2, 3 till infinity. Okay. The period, sorry, the orbit, periodic orbit with period 2 to the power k minus 1 t loses stability and a new orbit with period 2 to the power kt appear. Let us take k is equal to 2. For mu2, we see that orbit with 2t disappear and new stable orbit with 4t appear. Okay. So this is going to happen something like this. For mu1, the orbit with t, it is going to disappear and a new orbit with 2t is going to appear. This is what it is trying to say. So like if I try to write it like mu1 uh, parameter disappear, appear. We try to write it in the table. For mu1, my orbit with t disappear and 2t appears. For mu2, orbit with 2t disappear and 4t appear. For mu3, the 4t disappear and we'll have 8t appear. Likewise, it is going to happen. Mu k 2k minus 1t 2kt. Okay, this is going to happen till k or n value, let us suppose. What about that? Well, after that, this finite number is going to get converted into a large value. Okay, and with that, what happens is that the periodicity will be lost. Periodicity will be lost and the system will go to chaos. So that is what we call the period doubling route to chaos. If I talk about the bifurcation diagram, it appears something like this. 1, 2 period. Each period is going to bifurcate into other two values. Then again, other two value, two value, two value, two value. Likewise, it is going to happen, and at these point, it is going to lead to chaos, which will be just be the random occurrence of points. Okay, this is what we call the period doubling route to chaos. Okay, with this you will see in case of when we talk about the model, discrete model for population, there you are going to get it, and in various system also period doubling route occurs, like for the case of Duffing equation. The second could be the quasi-periodic route to chaos. Quasi-periodic route to chaos. So in quasi-periodic route to chaos, what is going to happen? First, one hop bifurcation is going to occur, which will be followed by the second hop bifurcation. Okay. And it will lead to two simultaneous periodic orbit such that the two frequencies are incommensurable. The two frequencies are incommensurable. What is the meaning of incommensurable? It means that the ratio is going to be irrational. The ratio is going to be irrational. Like for example, one is 2 and the other frequency is 2 root 2. So its ratio is going to be under root 2, which is irrational. So such that the two frequencies are incommensurable. What is this going to happen? This will lead to quasi-periodic response, and eventually this quasi-periodic route is going to lead to chaos. Okay. So this was the second one, and third one, which will help us to understand the question, which is the intermittency route to chaos. I suppose that this is one of the most interesting way which leads to chaos, because because in the earlier two cases we used to see that there is the whatever it is leading to chaos for a particular parameter value. The system is either going to have a periodic response, it is either going to have a quasi-periodic response or chaotic response. But in the intermittency case, what is going to happen is that for a long period of periodic oscillation, you will see that there is some burst of chaos, okay, which I plotted earlier also. Like for example, this is X and this is T. For a long period, I'm going to observe it. Periodic, periodic, periodic. Now, all of a sudden, for this time interval, my response is like this, and again it is periodic. So what is this? This is a burst of chaos. And what is this? This is a long periodic response. So I see that, okay, there is some burst of chaos. Here my system is actually chaotic. So then what will I do? The best way to talk about bifurcation is to change the parameter value. I will change the parameter. I will either increase or decrease the parameter. Now, when I will increase the parameter, what is going to happen? It may happen that this periodic response will again be periodic. But this time, instead of one burst, there are two bursts. This time, there are two time for which the chaos is there. And there is no periodicity. There is nothing like that after I can define a time period or I can define a time after which this burst is going to happen. It is just occurring randomly. Okay, so with increase of the parameter mu, the occurrence of chaotic burst increases. It increases and finally leads to mostly chaotic response with bursts of periodic and not I should not write finally over here and leads to. This finally leads to chaotic response. This finally leads to chaotic response. So this we call it as the intermittency route to chaos. I feel that this is one of the very interesting route to chaos because there is, intermittent occurrence of chaos, which finally it's like you have a periodic response. Your chaos came, it tries to capture the whole periodic response and is finally successful in capturing the whole periodic response, right? So for the question, that the intermittency of chaos in the system response may lead to chaos, the answer is going to be yes, it can lead to chaos. And you should always check if you design a system, you should always check that if there is some intermittent occurrence of chaos, you should always check with the change of parameter that is it leading to chaos. Okay, now coming on to question number 7. For a system with an initial deviation d naught and final deviation dt, it is observed for n parts of the solution curve that dt is less than d naught. Then the Lyapunov exponent will be, okay, no, it should be then the system response will be. Okay, so talking about a Lyapunov exponent, we know chaos is there. It can happen. Now we know that I can use Poincare section to know whether my system is chaotic or not. But there should be a quantity. Like for measuring the mass, we have the weighing scale in which I can say it is 1 kg, 2 kg, 3 kg or anything. For measuring the distance, we have the metric scale. Likewise, there should be some, uh, you know, value that could be used to quantify chaos. So this Lyapunov exponent is that quantity, which is going to tell me whether my system is chaotic or non-chaotic. Now, firstly, what is a Lyapunov exponent? So it is very beautifully defined by Wolf. You can read his paper also. He has done an incredible work where he talks about how to find the Lyapunov exponent for experimental as well as your this analytical system from the equation of motion. So for the Lyapunov exponent, I know the equation of motion. I can know the response. Now I have the response. Now I simultaneously simulate my system in such a way that for the given initial condition, I'm going to get the actual response and then I'm going to give a very small deviation in the initial condition and then we are going to have what is going to be the response as time proceeds. So if you remember that earlier when we used to get used to do the simulation for the system of equation where we used to know that whether my response is chaotic or not, we used a very important property of chaotic response, which was a highly sensitive dependence on initial condition. So what used to happen was that, as we saw it also, that when we gave almost 10 to the power minus 6 or minus 7 deviation to the initial condition, my chaotic response earlier for some period of time it was overlapping with the original response. But after that, the response was very different from the actual response. If you remember, I also discussed a case where the change in 10 to the power minus 6 of the initial condition, it led to, at a particular time, one response was showing the lowest value and the other was showing the highest value. Okay, so that is the randomness of chaos. So if I have such kind of a chaotic system, I can actually use this property of sensitive dependence of initial condition to try to find out the Lyapunov exponent. Okay, so for example, I have an initial condition x naught and I perturb my system to a new initial condition x naught plus delta naught, where delta naught is very, 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 very small than x naught. And I trace the curve of my system. Let us say this is xt and this is xt plus delta t. This is my delta naught. This is my delta t. So if my delta t is greater than delta naught, what does it mean? If there is a divergence, it means that my response is chaotic, because only chaos is going to show sensitive dependence on initial conditions. If you remember, I did that simulation to show you that for quasi-periodic or periodic response, even if I take 0.5, 0.8 or 0.9 deviation from the initial condition, the response was still the same, exactly same, right? But for chaos, that was not the case. So if I talk about my non-chaotic system, in that case, if I take x naught and x naught plus delta naught, then it is going to be something like this. Delta naught, delta t. So you see over here, delta t is less than delta naught, and here delta t is greater than delta naught. Okay, so on comparing which one is greater with respect to delta naught or lesser, we could predict whether my system is chaotic or non-chaotic. Not predict, actually, it's we could tell. Predict would not be the correct word. But this is possible, or we should, if we are taking the whole orbit and then finding out the value, it is making my system very sensitive. I want my system to be robust. So what will I do? I will divide my solution curve into n number of parts. Minded, as I increase the n number, my Lyapunov exponent is going to be more accurate. So if I see it for the n parts, I'll divide my curve into n parts, and then for every nth part, the initial point, I deviate by some small amount, and I calculate the value. Okay, okay. So if I calculate the value, and then I try to find out the Lyapunov exponent. Firstly, for this Lyapunov exponent is given as ln of delta t by delta naught. You know why we have used a logarithmic function? Very easy, because the best way to find the relation is logarithmic. Otherwise, what we had to do was we had to find the difference, or even if we are taking the ratio, it was a bit difficult, right? But now when we are using this, because this is the best way in which we should use finding out the Lyapunov exponent. So because the ln, if this inside value, if it is greater than 1, it is going to give me a positive value. If it is less than 1, it is going to give me a negative value. And on the basis of the negative value and the positive value, I could say my response is chaotic or non-chaotic. So for this, definitely my system response is going to be non-chaotic, and my Lyapunov exponent is going to be negative. And for this, my Lyapunov exponent is going to be positive, or the ratio is going to be greater than 1. Right? So it could say that my response is chaotic. Now, for the n iterations or the n part, if I divide, then my Lyapunov exponent is going to be divided by n. And here I'm going to take the summation of the Lyapunov exponents. Okay. So this is going to be the case. So when it says that for all the n parts, dt is less than d naught, which means that for all n parts, the value is negative. Okay. So if the value is negative, what does it mean? My system response is non-chaotic. And this Lyapunov exponent is a very nice, way of finding out or differentiating between the chaotic and non-chaotic, and among the chaotic responses also. Like if I have two kind of a chaotic responses for the same system, then I can use the Lyapunov exponent to find out a relation, or how we can differentiate between those two chaotic responses. Okay, because when we see two different chaotic responses in the x versus time plot, it's just random. We cannot find out any kind of a similarity or dissimilarity. However, when we plot the Poincare section, it could tell us that whether the attractor is changing or the attractor is same, different, and everything. But this is going to quantify the uh, chaotic response. Okay, so this was question number 7. Now we have to go to question number 8. Okay, so now I will connect to my laptop, because this we will take the question using MATLAB. Okay, so we are on the question number 8. Now the Okay, so now the question is all about van der Pol oscillator. Earlier we studied about the van der Pol oscillator, and we used a value of mu, for which we saw that there was limit cycle oscillations. Okay, but this time we got to know that okay, there is something like relaxation cycle as well. So this question is all about that. So we have a van der Pol equation, and we have 4 options, among which we have to select that which one is correct. So it asks about that for these 4 particular values of mu, whether we are going to have limit cycle oscillation or relaxation oscillation. Okay, so I've already written the MATLAB code, and I expect that you people can now write the MATLAB code, since we have done writing with it very rigorously. So coming on this, so this is the equation. So if we look at the first option for mu 6, so if I keep the value of EP. Here I have taken the mu as EP. Okay. And if I now simulate, wait, we'll see the equation. We have minus of Z1, and we have plus EP. 1 into Z 2. Yeah, that's fine now. See, okay. See the three plots. First one is the position versus time. Second one is the, okay, it should not be position. Second figure is actually velocity versus time. And the third one is our phase plot, which is velocity versus position. Okay. So if you see over here, what is this? It is not limit cycle oscillation. It is relaxation oscillation. So how are we differentiating between limit cycle and relaxation? So see, the relaxation also oscillation is also going to show isolated periodic orbit. The only difference is that in case of a limit cycle, we had a smooth variation of position and velocity. While in case of a relaxation oscillation, if you see over here, our one time period from here to here, if I say, it has the variation of velocity which is either almost horizontal or almost vertical, right? Which means that my one cycle could be divided into two time scales. One is a fast varying time and second one is the slow varying time, right? Like when my position is almost horizontal, the my velocity is horizontal, my position is going to change very slowly, right? But when the velocity is having a kind of vertical behavior, my position is going to change very abruptly. That you can see over here also. This change of position is very slow, but this change of position is almost vertical, very abrupt, followed by again slow variation of position and again abrupt change, which you can see corresponding to the velocity as well. And if you see the phase plot also, you can see that there is sharp curves, right? This smooth curve shows that the variation is smooth, and this sharp curve shows that the variation is very fast, and that is why it is not smooth, right? So the option 1 is definitely not correct because it says that for mu6 it is going to be like limit cycle oscillation. See over here, relaxation also oscillation is also kind of limit cycle, but this question we are actually differentiating between whether it's going to be a limit cycle or is it going to be a relaxation cycle. Okay, so we'll close the figure and we'll switch to the second set of value of mu, which is 0.1. See, in this case my phase plot is smooth, my velocity profile is smooth, and my position profile is also very smooth. So it means that it is not a relaxation cycle, right? It is a limit cycle. So my option B is correct. Now we'll come to the third option, which is eventually correct, but we'll just simulate and see. We have mu as 8. Definitely it's a relaxation cycle. You can also see one thing in relaxation cycle, that the convergence to the cycle is very fast as compared to the limit cycle or the lower values of mu, right? For the lower values of mu, the convergence takes some time. But for the relaxation oscillation, or when mu is very high, then at that time the convergence is almost abrupt. It happens just very quickly, right? Here again you can see that the velocity profile either almost horizontal, almost vertical, and the change of position, it is abrupt and smooth. Third option is correct. And the fourth option is definitely not going to be correct. We'll just check for that matter. 0.5. We have 0.5. See, the variation is not that smooth, but definitely it is smooth. It still does not, the velocity profile still does not have almost horizontal or vertical lines. So it is a not a relaxation cycle. So option D is not correct. So now we'll go to question number 9. Okay, chaos can occur in which of the following systems? So we have three options and we have to talk about that chaos can occur in which of the following systems. So this I will not be discussing much because I think that in the class it has already been discussed that for a given equation, how will you see whether chaos is going to occur or not? So this I believe you people can do on your own. What I would like to tell over here is that for a system, there should be some softening and hardening behavior, both together, so that it could lead to chaos. Because if my system is very, it is having hard for stiffness, in that case, as my amplitude is going to increase, my system is going to get converged very soon, right? So it could prevent such random motion. Okay, there should be optimization of both in order for the chaos to occur. Okay, we'll go to question number 10 directly. Okay, a system with equation will lead to chaos for changing parameter f through which route? Okay, so we have the equation and we have to change the parameter f and we have to know which kind of a route it is going to take. So I've already written the code and I've taken the initial displacement as 1 and the initial velocity as 0, and now I will run the code. Okay, maybe we can change because it is directly going into chaos, because we want to actually see first that which kind of a route it is going to take. Now see, this is the phase plot, velocity profile, position. Do you see, after the initial transient, it is going to a periodic response. However, we are still not convinced, so we'll do one thing, that we'll plot it for 200 to 300 time. Okay, so we'll know whether it is, because here we cannot say whether it is periodic or not, because if periodic, it should be a single orbit. So Now it is a single orbit in the phase plot. So definitely it is a periodic response with a period T. Okay, we'll close it. We'll change it from 0.2 to 0.28 and then we'll simulate. Now, from the phase plot, we cannot say as of now because nothing could be said because it has the transient and the steady state as well. We'll come to figure number 1. And here you can see that the response is periodic. However, there is two peaks and two crests. So what we will do, we will just plot the steady state response. Now you see there are two loops, which signifies that we have a period doubling. Yes, the period is now doubled and we have a orbit with time 2t, time period. It is periodic, but the oscillation period has changed to 2t. Now we will change it from 0.28 to 0.29. Again, now I can see 4 peaks and 4 crests. So we'll plot the steady state response. See, now I can see 4 loops. Okay, so now my 2t is changed to 4t. So now I can see that yes, it is going through the period doubling route. Definitely it is going through the period doubling route. We'll take 0.35. We'll run the code. Now see, earlier it was having just the positive values. Now it is going to the negative as well. You see over here? Now there is some different kind of a behavior. So we'll again plot the steady state response. Now do you see what is happening? There is change of the system behavior, right? And now we can see that since the amplitude has increased a lot, so now the chaos is coming. Now over here, if you'll see, there is again period doubling. See, earlier these two small loops were not there, but now they are here. Now we'll again change it to 0.38. Again, we'll simulate. See, there is some difference in the behavior, but still I can see the periodicity. Now see, the response is different from earlier. Likewise, when we'll keep increasing and as soon as we reach maybe 0.45, now I feel the chaos. Yes. But how will I know whether the chaos is here or not? First, we'll do the same approach which we were doing. We will plot the steady state response and see if there is a single line or not. No, I can see that there is no single line. Apart from that, what you can also look into while predicting about the chaotic behavior is that this open end. You can see here there is an open end. For a periodic response, this open end you are never going to see, right? Because it's a closed curve. There is an opening, which suggests that it could be chaotic. So what will we do? We will do the best way we know to test chaos. we'll solve the system, and then we are going to give small variation in the initial condition and again simulate the system. If my system, see, if my system is going to have the same response as earlier, it is non-chaotic. But in this case, that is not happening. For some initial time, my system is showing exactly same response, but after some time, it starts diverging from the before response for just a very small variation in the initial condition. Earlier, the same, but after that, there is divergence in the response, which suggests that my system is now gone into the chaotic motion. So what do I know? I know that through the period doubling route, my system went from period T to 2T, 2T through 4T, 8T, and then into chaos. So for this question, my answer is going to be period doubling. Okay. So I hope all of these things are clear to you, and I hope that this will help you for solving the assignment problems. However, I feel that I have uh, taken questions which are tougher than that of the assignment problems. This time the assignment, it seems that it is very easy and you can solve it very easily. So if there is no doubt, then we can end the session. Okay, I suppose that there is no doubt. So, okay, then we'll meet next week again on Tuesday, 6 p.m. to discuss the next week's problems. And for today, thank you and good night.